All right, I'm going to get around to doing what I really do with this test equipment that I've built, this active load, and that's developing gear. We're going to look at the regulation inside a device. Every digital device has a bunch of regulators in it. These work just like what we've seen in the power supply stuff, but you've got anywhere from 3 to like 10 switching regulators inside a piece of equipment that supplies all the digital voltages 1.8, 3 volts, 5 volts. All of these voltages have to be regulated, and they're just like the power supplies that we've already seen. So the same principles all still apply. What you're really looking at, I'm not sure we can see it super cleanly here, but that's a regulator, that's a regulator. There's 1, 2, 3, 4. There's 4 on that board, 5 on this board alone, right? So that's what you see on these things. And these are switching regulators, which are just like switching power supplies that we all have learned to dislike. And there's a really good reason why switching power supplies are bad. So the first thing we're going to do is we're going to look at a switching power supply and see all the garbage that comes out of them and why they're bad news. So I've got an Apple TV that I've opened up, and I've stuck a couple of leads on the power supply, the voltage regulator that's inside the unit. I put a little heatsink on so I don't melt the CPU. I do this a lot with gear. So what I can do is I can hook the active load directly into circuits, and I can then examine what's going on and how the power supply works in that circuit. Also, obviously, I can look at noise. Noise is a huge issue inside these units because the engineering just doesn't care. As long as it works, they just don't care about the amount of noise and the garbage and stuff that comes from it. Okay, so what I'm going to do is there's a couple of things. First, I want to show you how a switching power supply works. It's pretty simple. Think of a bucket full of water. You punched a hole in the bottom of the bucket so there's water that's coming streaming out of the bucket. Now, you want to keep the bucket at the same level. So what you can do, what a linear power supply does, is it feeds in, it senses the water level. It senses the water level that's going on, and it feeds in the right amount of water to keep it where it needs to be. So if it drops down a little bit, then the linear supply fills it up. If the rate going out of it goes faster, then the linear power supply fills the bucket with more water. So its rate is completely analog, and it keeps all this really level. Now, how a digital a switching power supply works, a pulse width modulation power supply, how this works is your bucket gets full, you got a hole in the bottom, and it senses when it goes down a certain way, and it spits a blast of water into the bucket. And the more water that's needed, the more blasts that there are into it. So it does these pulses of water into the bucket in order to keep it full. The advantage to this system is that it's very efficient. You don't lose any, it's very efficient. There's no heat generation. It's much easier to put on a board. There's just a whole bunch of things to it, but that are good for manufacturing a device. And good for profits rather than good for performance. So switching power supplies are universal everywhere. If you have a digital device anywhere, it is filled with these types of switching power supplies, which switch the water on and off to fill the bucket, rather than just simply linearly applying an amount of water to it to keep it level. There are 2 types of switching. There's one where it's the same length of blast of water, but you just do it more often. And then there's a type of supply that changes the length of each blast. So it gives it more more water in each pulse. One is pulse width modulation. That's how long it is. The other, I don't remember what it's called, but it's you just send a whole bunch of pulses. Now, this is a huge mess because these pulses are a certain width. So they produce all sorts of artifacts, and I'll show all that in a second. So the Apple TV, the main supply that it has, which is producing the 3 volts that the CPU needs, we're going to look at the supply that goes to the CPU. And we're going to inject test signals into it. But before we get to injecting test signals, we got to look at what's there, the noise and the garbage that's already there. And that's actually a lot bigger of a problem than you might think. Okay, so I've kicked on the Apple TV. Now, on this scope up here, I'm going to go ahead and move the camera. This scope is hard to catch. A good analog scope is hard to catch on a iPad, but we're going to give that a whirl. Because an analog scope is the only way to really properly look at this type of a signal that I'm going to show here. So what we're going to do is we're going to look at the actual signal that's coming out of this switching power supply. We're going to look at the switching itself. Now, what we're seeing here, it's a little confusing to look at. We'll zoom in just a little bit. But, whoops, I swear. So what we see here is we see a pulse. That's this big line right at the beginning. That's a big pulse. And what that does is that's what's really going on. That's filling the bucket. So it fills the bucket just a little bit to make up for what's coming out of the bucket. Then it turns off. But there's all this ringing that occurs. This is a massive amount of noise. And then what we see is, although it's really diffuse and hard to see, there's this same pulse, the same width pulse going on here. And the more pulses there are per second, then the more water is going into the bucket. Okay, so in this case, the more pulses you put here per second, the more current is going through it. So this is how it regulates it. What it does is it's putting less pulses if there's not much juice and more pulses if it needs more. Now there's obviously all this ringing and all this noise that's going on. Now this pulsation that you're seeing going, 1, 2, 1, 2, 1, 2 is actually my active generator. What it's doing is it's doing a 1 hertz pulse. So it's going, well, it's half hertz. So it's going on, off, on, off, on, off, putting a small amount of load on the power supply. So when there's more load, then the pulses get closer together. You can see that more like this. So you can see there's a whole bunch of pulses, and those are the pulses that are filling up the bucket. And when it needs more juice, then it does them closer together. So that's how it works. But you can see that the amount of noise coming out of this is ridiculous. So that's how a switching power supply works. This noise is radiated. So what I'm going to do is I'm just going to put the probe close to the device, not actually touch it, and we can see this noise even from a ½ inch away. So this noise is radiated out into all the other circuits around here. So that's, you don't want that. Anyway, so that's how a switching power supply works. So now what we're going to do is we're going to look at sort of the aftermath. So we're going to back up and we're going to look at the other scope. And I'm going to talk about that. Now, this is actually, I've got it just freeze framed, and we're just looking at noise. So we're just looking at the voltage noise out there. Now what I'm going to do is I can grab individual pictures. So I'm pressing it and I'm grabbing stuff. Now this is the actual noise. This is significant. This is, 8-10 millivolts of noise, and this is the switching frequency. So this is this setup, this pulse here, this stuff is the switching that's going on. Now, the bucket can't do any better regulation than the speed of its little spurts into the water. So there's a limitation to how accurate this can be based on the frequency that it's working on. Also, this frequency ends up in the output. That's what we're looking at. We're looking at the noise output of that regulator. This is what's actually going to the CPU. So even deep inside this completely unmodded Apple TV, we've got 22 millivolts of just noise right there, but it doesn't stop there. If we keep popping this, you'll see some of them are much cleaner. Some of them have a whole bunch of real high frequency noise. So there's a real wide range of noise coming out of this. This one's 40 millivolts of noise just from the switching power supply that's in there, the switching regulator that's in there. So this is a huge mess. And this is, you see this in every single digital device I've ever seen. The manufacturers, even high-end manufacturers, really don't address these switching regulators. And this is really a problem, because this is, causing voltage variations and a bunch of noise that goes into the digital circuits and causes jitter. This stuff radiates noise. There's a million reasons why this is just bad news. Okay, so now what I'm going to do is let's back up and let's reset all this, and we're gonna look at what I'm actually doing current-wise, and we're gonna look at how the regulator is actually functioning like we were in the other ones, on the other videos. So so what I need to do is go back to run. So this will take me a second just to get this set up so that we can use this properly. And this is what I'm doing here is a very, very low frequency. So this is 1 cycle per second, or half a cycle per second. There is so much noise on there coming from the switching regulator. It's hard to even see these small current changes. Let me put up some current changes so we can see what we're doing here. Okay, so what we need peak to peak for our current. And we need the pulse width for that current, so we know where we are. Oh, whoops, that was the wrong channel. Well, digital crap, always has too many buttons. I really prefer analog gear. Okay, so we're going to go peak to peak. Let's go look for our peak to peak. All right, and we need pulse width. Okay, so now what we have is we have these numbers that we've used before that we can figure out stuff. So what I'm doing is I'm giving it 100 well, we can't tell right now because there's so much noise, but I don't know, we'll find out how many milliamps of pulse. So what I'm doing is I'm doing a pulse into the Apple TV power supply to see how it works, and from there I can apply a bunch of changes to it in order to be able to perfect this so that the regulation right into the CPU is just way, way, way better. So in order to even see this signal, because it's such a mess, I need to do a couple of things. I'm going to need to average this out to even see what's going on. Now, because this is a low frequency, this is going to take a minute for this to average out. So let's go ahead and let that average out, and we'll go ahead and look at how it's working at these low frequencies. So this first test is going to be the on, off, on, off, on, off. So what's going on is we're adding a load, taking it away, adding a load, and we're going to look and see how that works with the noise. But we have to look past all the noise that's being generated by the switching power supply. So actually this will take forever, so let me just go up in frequency. So let me just go up to 1 kilohertz, where we won't be just incredibly bothered by these delays. Okay, so now, whoops. So let's go ahead and take a look at the pulses like we're used to looking at. Okay, this is still kind of set up for the other thing I was doing. So you'll have to give me a second to get this all set up correctly. There we go. All right. Okay. So this is our pulse at about 90 milliamps, and because the averaging now can do much quicker, you can see the amount of noise when I click it. And then it has to get rid of that noise. It averages out the noise. The scope does. So now we're looking at. Let me flip the input around so we can see it correctly. Okay, so now what we're looking at is we're looking at the pulse right across the regulator right to the CPU, and we're hitting it with about 90 milliamps of current, and then we're looking at the amount of noise, and we've removed all the extraneous noise, or most of it that we can, in order to be able to see our signal. I'm doing that with external triggering and with averaging on the scope. So it's not performing horribly. The regulator isn't. It's got a lot of turn-off noise, but you can see this ringing. This is the switching power supply, and it's not able to do this well. So that's the ringing that's going on here. Let's go up to a higher frequency. We'll play with that. So now we're going to go up in frequency. Now what's going to start to happen here is these kinds of regulators and circuits don't do very well at high frequencies. So we're going to see huge messes start to develop. I'm not even sure we can pick that one out of the noise. So it shows that it's really, this regulator is really not even working at a 5 kilohertz equivalent. So this is a 16 microsecond pulse, and it just looks sloppy. It's just a huge mess. The noise is just really just a mess there. So it's doing very poorly. So this regulator, this pulse width modulated regulator, is doing a really bad job and is very frequency limited. It can't go up and get the really tiny pulses like what you really need, simply because those little spurts of water into the bucket are too big to get small changes. So they can't do a good job of it. So so these types of regulators and these kinds of circuits are usually really awful like this. It's very typical. You know, at lower frequencies, they do well. They do fairly reasonable job. Here's an example. This is like 100 hertz equivalent, so this is about 4 milliseconds, and that's doing pretty well. So that's, it's got a little bit of overshoot, but overall it's supplying the amount of current. The voltage is quite well regulated generally. It's not doing too bad a job. But at the higher frequencies, at the smaller pulses, it does a terrible job because it's a switching regulator, and switching regulators have issues with higher frequencies. Supposedly you take care of this with caps, but you can't really take care of that. You really, as you can see here, you really have to get away from this kind of whole design, or at least you have to look at it, and you have to really design things more properly for it. The other thing that happens here, we're looking at a 60 milliamp pulse, which is typical for what it does for streaming video. So this is what I would expect if I was streaming video. This is the kind of pulse of current I would expect from the CPU. But all these characteristics change with the amount of current. So if I go up in current, so now what we're going to do is we're going to go to a more juice. Now this is at a lower frequency, but we start to go up in frequency, smaller pulses, things get particularly bizarre again. And this is a really compared to what we were doing before, this is way worse performance. So now you can see that the amount of noise that's coming out of this thing is actually, I can't get down there that low. Whoops. I could if I grabbed the right knob. So now we're at a really high amount of noise for that same 5 kilohertz equivalent. So it's generating a lot more noise as we draw more power. And this is 180 milliamps, which is what I expect if it's doing a more complex task. So as it's changing voltage, it's really changing characteristics because of the switching power supply, the switching regulator. Now these things cascade. So what I mean is, like the main power supply has all of its characteristics, all of its different idiosyncrasies. Then what you have is internally, you then have a voltage regulator internally, which has all this weird, strange stuff. And each, like the CPU, a CPU might take 3 or 4 different voltages, all with different types of regulators, all with different characteristics. So all of these things combine to where any kind of digital device that you're using right now has got this huge mess going on the board. This is what I address. So this is what I use this for. What I do is I use this to really explore what's going on into each area of the device and really optimize all of this stuff to where it's just working way, way better. So using the right kind of test equipment, then this is fairly straightforward to deal with, but you gotta have the right test equipment. You gotta know what to look for, and what's nice too is I can make changes and look at the changes so I can refine all of it. There's something else I can do with this setup. There's 2 other things I do with this setup. One of them is I can induce noise and see what it does. So I can induce noise into a CPU circuit, and then I can go look at or listen to what that does. That's been super critical for learning a whole bunch about other things. The other thing that I can do is what's called TDR, time domain reflectometry work. So what I can do is I can send a pulse into the circuit, and I can look at the timing of how it hits other parts of the circuit, learning an awful lot about what's going on, kind of like sonar, and looking at what's in between you and the boat. You can see everything that's going on in there. So this device, my active load, is extremely useful in what I'm doing, and I don't believe there's anybody else doing this kind of work on gear. And I've been doing this for, wow, I don't know, 10 years? So for me, all this is just routine. And that's why the Apple TV and the Switch X and everything were really quite easy to get to the levels where they are, is because, I'm doing stuff that other people aren't even looking at. Anyway, so that's kind of the general feel of all this stuff.